Alright, welcome to the NUPOC video study guide number 91. Let's do another pulley problem here. This one's a little bit different. Instead of just having a mass hanging off of some pulleys, we actually have a block that's sliding on a plane like this, and there's some coefficient of sliding friction since this block is moving up the plane with constant velocity, and we know the angle of the plane theta, and we want to find the tension in the rope, which is the force that we're pulling on the rope with at this end to get this block to slide up the plane. Alright, so first thing we're going to do, just like we've done with our previous problems, is first we want to recognize that it's still a statics problem because we have no acceleration. And so we can go ahead and sum forces in the different directions, right, and set them equal to 0. I'm again going to draw our coordinate system here. In fact, you know what I'm going to do? Like we do for other inclined plane problems, right? Sliding block problems, we want to make sure that our coordinate system sort of lines up with the plane. So I'm going to call this x hat, and this is y hat, like that. So if we did the right hand rule, our z hat is going into the page like this. Anyways, okay, so let's take a look at this block right here, M. And I'm going to draw it. I'm going to draw it on the plane. You know what? Now I'll just draw the block like this, right? There is an inclined plane problem. I think maybe a couple of them back in the regular physics, statics, and dynamics section, or basic physics section, whatever the playlist is called, I forget. But anyways, let's go ahead and do the same analysis we would for an inclined plane problem. So we have mg pulling directly down here, but let's split that into two vectors, right? Let's split that force mg into two vectors. So we have some force, let's call it Fy and Fx, right? Okay, so we know that this angle is theta if this angle is theta, right? And that's the angle of the inclined plane. So we can say that if this vector is mg, then Fy, and again I'm just using magnitudes here, so I'm not going to worry about the direction since the tension in the rope is what we're trying to find, and that has a different direction depending on what segment it's in, so we'll just use the magnitude of all these forces. So Fy, right, is going to equal cosine, right, or mg times the cosine of theta. So let's just write mg cosine theta, and Fx is going to equal mg sine theta. Okay, and now we have this, what I'm going to call F2, because it's the force in this connection between the mass and pulley 2. We have F2 pulling up, and we do have friction, so I'm going to draw it acting at the base of the block here, right? And that is, I'm going to call that FF, force of friction, right? And we know the force of friction, that's easy once we know what Fy is. Fy is the force of the block pushing down on the inclined plane, and so it's not sliding in this direction, so there must be a normal force pushing back from the plane, right? So it's equal in magnitude to Fy, so we can just go ahead and say that Ff is mu k times Fn, which is our normal force, which is equal in magnitude to Fy, so we can just say this is mu k mg cosine theta, right? Okay, and F2, we know that the block isn't accelerating going up the plane, it's at a constant velocity, so we know that F2, right, if we're summing the forces in our x direction here, must be equal to all the forces acting in the negative x direction, right, which is FF plus mg sine theta. Okay, so, and I'll sub in what FF is. So we can say F2 is actually UK mg cosine theta plus mg sine theta. Okay. So we need to basically just relate F2, the force in this connection here, to Ft. And that's pretty easy. That's what we've been doing now for the last couple problems. So we have F2 pulling down here, and we have Ft pulling up on both sides of the pulley. So we can say that F2 equals 2Ft, or Ft equals F2 over 2. Right? And we know what F2 is in terms of mg. So let's just go ahead and write. I mean, we're just going to divide this by 2, right? So let's just go ahead and do that. And we'll say that the tension in the rope, you know, the force we need to pull on this rope to get this block to slide up this plane with this angle and this coefficient of sliding friction, right, to get it to slide up the plane at a constant velocity, is simply, I'm going to factor out mg, right? I'm going to factor out the mg out of both these terms. So it's just mg over 2 times UK cosine theta plus sine theta. Right? So maybe we can see obviously that as theta approaches 0, right, this term is going to go away here, and the force will be dominated by the friction, how big the friction is. We can see as it approaches 90, right, this term will go away, and the force will just be dominated by the mass itself. I mean, if we went all the way to 90, it would just be a hanging, you know, the mass would just be hanging there next to the ramp, right? And of course we can see as mu k increases, right, it's going to increase the tension on the rope as well. So thanks for watching, and as always, don't forget to click down here to subscribe so you don't miss out on the upcoming videos.